Hello. Wow. Can you hear me if I don't talk into that out of curiosity? Is this pretty good as well, or should I use the microphone? Do you prefer this or this? Or somewhere in the middle? With the microphone? Cool. Sweet. I'm glad that some people have shown up to listen to something about Rust today at a Java conference. I'm a bit excited about that. It's also late in the day, so I assume that's why we don't have so many people that are enthusiastic, or at least that's what I'll tell myself. Anyway, welcome to this talk today on 10 things Rust could learn from Java and 5 things Java should probably steal back. I'm Scott Gerring. I've been writing Java professionally since Java 6, and I think in university we're on Java 5, which was a very long time ago at this point. And more recently, I've been writing Rust in kind of a personal capacity for quite a while, and in a professional capacity at Datadog for a couple of years now. Out of curiosity, has anyone here heard of us? Datadog, or Datadog as everyone else pronounces it? A couple. We do observability and security for modern applications and infrastructure. There is very little of that in this talk, but if you're interested in hearing more about the company, come grab me afterwards. Now today we're going to be looking at why Rust is interesting from the perspective of seasoned Java developers. And for that, we're going to need something to build to try and make it a bit more concrete. And because in the past, for a number of jobs, for some unknown reason, I have built imagery hosting systems, think like the backends for Google Maps and OpenStreetMaps, we're going to do that. There's also an interesting element of performance in these systems, which makes it kind of particularly amenable for Rust in comparison to other things. And most companies that do this build things in a very typical fashion. You have the main API, which is the imagery one in the middle. You have a tile pyramid. It gives you tiny 256 square pixel images of the tiles. You slide around on your maps and you see them. You typically also have an API that gives you metadata about your tile sets. You know, this is satellite imagery, this is vector tiles for OpenStreetMaps, that sort of thing. And then some other APIs for uploading things and for fetching lots of tiles at once to do pretty mosaics. In most cases, you will have object storage as a backend for all of the imagery, so you break things up into tiles, you chuck them in S3 or what have you, and you have some spatial queryable database like Postgres, or in this case SQLite, to chuck the metadata in. And as I mentioned before, latency is a thing you care about a little bit here. And the reason for that is that Google set very high standards with Google, with the Google Maps experience. You slide around on the map, everything loads really quickly. If you build another service to do this, because your company captures satellite imagery, for instance, you really need to meet that experience. And when things are slow, because your service is badly written, say, you have this really visual jank like this. Some tiles load from a different zoom level, some tiles don't load. People get sad and get angry because if Google does it, why can't you? So this is an interesting domain for languages that try and focus on performance. I'm really trying to give Rust a bit of a heads up, a bit of a leg up here to say like, hey, we're doing something that you're meant to be good at, let's see how that plays out. And this is also something where internally at Datadog, we've seen a great amount of shifts from Golang primarily and some Java to Rust. We have lots of customers, we do observability on their behalf. They emit data at a high rate, for instance, in metrics, numbers about your systems over time. And we try and suck all that data into Datadog as quickly as we can, so their alerts can go off and say your service is down, or their dashboards can show that everything's healthy. And in one case, we had something that was running with Golang for years and years, but the cost of it went up and up and up, and the resource consumption went up, and we said, hey, maybe Rust is going to be helpful here. What we ended up with was reducing the tail latency of the ingestion for those metrics by 60 times, which is pretty ridiculous, and halving the amount of resources that it needed to consume that. These are like kind of ridiculous numbers. I think there's some links at the end of the talk, and I'll post them in the companion app as well. They kind of go into detail, but it's really a use case it's lending itself to Rust. I'm not saying this is like the typical outcome, but in some cases it can be a really nice advantage. And the other thing with Rust, apart from it being kind of associated with performance, is that there's like this ridiculous culture on the internet at the moment of people being really over-the-top Rust maximalists. And on the one hand, I think this is kind of funny. I like it when people have really strong opinions about things. It's like entertaining chats at the pub and whatnot. But on the other hand, it can also put people off who are using well-established languages that they've been productive in for decades and decades at this point with Java from being interested at all. And I think that's a bit of a pity because there are some interesting ideas in Rust that are probably going to bubble through into other languages over time. So what is it exactly? It started off as a side project from a gentleman named Graydon at Mozilla for no particular purpose. And a couple of years later, Mozilla, which was at that point largely written in C and C++, the browser itself, they were saying, hey, these segfault things, pretty unfortunate, especially for a thing that's running untrusted code from the internet. We hear Graydon's been working on something, let's see if we can use that here. And it kind of came from this perspective of let's do C, but not make it miserable and not have seg faults all the time. So it started with a very kind of systems-oriented flavor, but it's worked its way further and further up the stack. You see it in the kernel these days, quite famously, but also in applications like Discord, ripgrep, fancy terminal tools that everyone's going crazy with because of Claude. Obviously, it's also not the first time that as an industry we've tried to make C again, but better. I think in some regards, Java also came at this with the approach with the garbage collector. Our kind of contemporary peers would be Go, which is also a garbage collected language, and Zig, which again has manual memory management, but a bit less awful than C, I would say. But the kind of thing that sets Rust apart is this idea of zero-cost abstractions. We want to be able to use this language and work at a higher level of abstraction than C. C is good fun. You can do wild things and cast pointers to all sorts of different types and nobody will stop you, but the failure modes are obviously awful and most of us don't want to work at that level. Like most of us don't want to write C. And the first high-level abstraction people think of is typically memory safety. If we compare that to C, C doesn't care. You can do whatever you want. It's unsafe. It's good fun, but the seg faults are an awful outcome of that. Java has safety, but it pays a runtime cost for that through the garbage collector, so we get to ignore a lot of things, and there is a small runtime cost for that. And Rust is trying to make this work by proving the memory safety at compile time. So by forcing you to structure your code in a particular way, the compiler is able to automatically free memory for you where it needs to, while letting the values behind that memory remain available for the length of the program as they have to. Another kind of example of this zero-cost abstraction idea is generics. In Java, we do type erasure. In Rust and C++, we do monomorphization, if I'm saying that properly, but the idea is the compiler is basically copy-pasting the generic code at compile time for all the different types of values you expand, which means there's no runtime dispatch cost, which is very small, but in some cases matters. And traits, which are the interfaces in Rust, are statically dispatched, which means that the compiler knows exactly which variant of a function to call at compile time, so you don't have things like vtables. You don't have to look up, I'm doing this object, so I have to call over here. Again, it's a small runtime cost typically, but in some domains this matters. And because Rust is saying, hey, we're doing zero-cost abstractions, it's basically a non-starter. So let's build this thing twice, at least at a high level of detail, and kind of see what we pick up about the two languages as we go along. And I've used Quarkus on the Java side because I am an enormous Quarkus maximalist, but there's nothing in here that you couldn't do with Spring Boot as well. It's just kind of the framework I've used to build the app around. And full disclosure, I really didn't expect to get a talk about Rust up at Devoxx for obvious reasons, the conference focusing on Java. And when I did, I started to write it with the kind of 10 things versus 5 things angle, and it turns out it's really hard to have a 40-minute talk with 15 things in it that doesn't suck, to be totally transparent. So rather than doing that, and I hope this doesn't disappoint anyone too much that was expecting a list of like 15 bullet points, I'm kind of like arbitrarily awarding points to either language as we go through that add up to 10 and 5, based on my sense of what's important. I think it works better this way. The numbers add up in the end. I hope no one's too disappointed. Anyway, so we want to get started with Rust. We're Java developers. The first thing we do is go and Google, what web framework do I use? What is my Spring or Quarkus equivalent? And because it's Rust, we get a pile of results back, lots of strong opinions, and lots of people that are really, really obsessed with performance, because that is the way the community is. It's not super helpful, right? So you can kind of go and jump on the equivalent of Maven Central, which is crates.io, and you can hunt down some of these different libraries and say, look, who's actually using what? And it quickly jumps out that for web frameworks, everyone's using Axon. Well, not everyone, but like the majority of the community, so we'll pick that. For database access, we have SQLX, which is a bit of a lower level abstraction, but wildly more popular than the ORMs in that list. And then for observability, we need 3, which is kind of janky, and I'll come back to it later on because it's worth attention. And when we grab all those dependencies, we end up going and writing them down in a cargo.toml file, which is our definition like a POM. We have to stitch them all together individually. We don't have a bill of materials or anything helpful like that. And you'll also notice here that the things that are in red, these are all pre-release. And this is the way it is. Things in Rust, libraries in Rust, we're all super hesitant to ever declare them stable. And this is kind of funny to start with until you start chasing your tail every time things upgrade and you have to go and deal with all the breaking changes because nothing's stable. So it's worth calling that out because this is really still a bit of a rough edge with the ecosystem. If we compare that to what we do with Java, it's pretty simple, right? Like with Quarkus, you say, I would like an application. I would like a bill of materials to line up all my dependencies. And I also need one for object access. I need database access. I probably need Flyway for DB migrations. Finished. And if you kind of compare these two approaches to getting started with an application, it's pretty clear that Java really gets you off on the right foot, right? You pick your ecosystem, you do Spring, you do Quarkus, you do Micronaut, you jam together all the different things that the ecosystem has promised you fit nicely together through a bill of materials, and you are happy. You are confident that you have done something that makes sense. With Rust, that's not so much the case until you develop a bit of a taste for the ecosystem. So arbitrary 2 points to Java for this. It's just much easier to get started as it is today. And once we've done that, we're going to need to actually build an application. The main way of interacting with the Rust ecosystem on the command line is cargo. This does your builds and releases and creation of code and whatnot. We say we want a binary application. We could also ask for a library. Rust compiles to native executables. There's no JVM, so you can build this thing and run it on your Mac, but it's just for your Mac. And it also includes a couple of tools that everyone uses out of the gates. We have cargo format, which is the de facto standard for formatting code. Everyone uses it for everything. You never look at code and say, why are they using this silly other code style? It is just done and arranged with cargo format. And Clippy is the standard linter. You can also ask Clippy to fix things. So for many lints, it has kind of an expansion rule in it where you go through and it says, hey, this is wrong. You're not consuming the value of this function call. Assign it to the unused value type. Would you like me to fix that for you? And you can pass fix to it and it just fixes your code. This isn't for everything, but it's for a lot of them. And it really reduces the friction you have working with the linter. So once we've done that, we get to our first kind of main bit of Rust. Who's actually written some Rust before, out of curiosity? Cool. So this will be pretty unsurprising for that subset of you. The first off is that Rust has macros, and these are kind of like aspect-oriented programming in Java in that it lets the compiler transform code for you, but it's a core part of the language and it's really heavily used in the ecosystem as well. So in this case, we're asking for Tokio, which is kind of the de facto standard async runtime for Rust, to turn this async main function we have here into a regular synchronous main function that the operating system can actually launch. So you can imagine it's creating a thread pool and then pulling the futures from this function. Next up here, we see that this returns a result with the unit type, which is the two brackets. In Rust, you don't have exceptions. If you have code that is fallible, you have to model the fallibility of the code in the return types of the functions, which means you generally use this core result type that either has an error type or a success type. In this case, we're using a popular third-party library that means that we don't have to write the error type explicitly, but we can see from the signature that this function may fail, and if it succeeds, it returns nothing. Down here, we benefit from that. So we're saying, hey, let's load the configuration from the environment. The question mark is saying, if this is an error, propagate the error up, and we will look at how that works later on, because it's all nicely type-checked and handled in a really satisfying way, I think. But if it's successful, put it in config and move on to the next line, and so on through the function. Whenever we have failures, they're handled off to the side, and we end up reading the happy path as we go down. Here we're doing the same sort of thing. We know it's fallible because we have the question mark, and we're also awaiting the future. That gets handled by Tokio for us. And finally, we can actually start up the web server. So for this to be useful, we need to be able to pass some state through to our different request handlers, right? We have a function that takes a URL, like retrieve the tile from this. We need to be able to give it access to the database, to S3, and to some other configuration for our application. And with Axum, we do this by creating a app state struct, so a thing that collects a bit of data together for us. And we have to mark it clonable so that Axum can give it to all of the different threads that Axum is using to serve our requests. In Rust, you can't just have a variable and share it between threads. This is absolutely forbidden. And there are different ways you can go about handling that depending on what you're trying to achieve. In the Axum case, Axum says, we will do this by making it so that everything you give me to share between threads has to be something I can copy explicitly. This derived clone is saying, for the clone interface, the clone trait, provide a default implementation of it for app state that lets us copy this. And when we put that on, we get an error from the compiler. And it's basically saying, hey, you want app state to be clonable, but I can't make it clonable because your custom type app config there isn't clonable. The two library classes that we've used, or the two library structs we've used, are our custom one, is it? A nice thing with the Rust compiler these days is that it really goes to great lengths to push you in the right direction. So here it's saying, hey, maybe just make it clonable. So we can do that. We add clone to it. We also add debug, which lets us do a toString on it. And we can go and get the config and pass it into app state. And then we use it immediately again afterwards to pull the config, host, and port to form the URL that we're going to listen on with the web server. And here we get the next error and our first encounter with Rust's famous and sometimes feared borrow checker. It's basically saying, hey, you use this config variable on line 5, it's now owned by AppState, you tried to use it again on line 8, you are not allowed to do that, that is not on. And as people who have used any other programming languages, this is kind of ridiculous, right? Like, are you saying that I can only ever use a value once? And the answer is kind of, but in a way that you can deal with. But the gist of it is that we have this mechanism in Rust called the borrow checker. Its point is to prove that you have compile time memory safety by imposing some rules on the way you structure your code. And if you satisfy these rules and your code compiles, then the compiler knows where it has to free every value you've ever allocated. And this is cool. It means you don't need to do it yourself. The compiler works it out. And you don't need a garbage collector because the compiler works it out. You just have the friction of having to know how to make it happy. And there are a couple of rules. The first is that you have a value and it has one owner. And when the owner goes out of scope, the value is dropped or freed. An owner is like a lexical scope in the code. So you can imagine the body of a function between the curly brackets in a loop. This is an owner. So when you get to the end of a loop, if the value is owned there, it is dropped. If you get to the end of a function, if the function owns the value, it is dropped or freed. When you assign a value to another name, it transfers ownership. So we saw before in the code that we passed it into our runtime instance of AppState. We are giving ownership of our config to AppState at that point. We can't use it anymore below because it is now owned by AppState. It turns out that in lots of situations when you are programming, you need to use a value more than once, unsurprisingly. And we can do that by using borrows. This is basically a way of saying, hey, I'm a function, I need to take, for instance, config or a string or something, but I don't need to own it. I'm going to give it back to you when I return. And rather than having to explicitly return ownership, you can just annotate an and on the function signature and it gives it back to the caller. You can have lots of immutable borrows of a value, but you can only have one mutable borrow. And this is something that feels a little bit abstract here, I think, but once you start looking at how we deal with concurrency, it becomes clear why it's there. So with that out of the way, and this is a super surface level coverage of the topic, I think, but hopefully enough to get on. We can look at this again and we can say, hey, on line 5, per what we understand and what the compiler suggests, we can just copy config, right? We can make a separate copy of it. AppState can own that. And down on line 8, we're free to use config again. And this is absolutely fine and will compile. But if we think a little bit more about it, we can also do this. We can say, hey, when we format that string to generate the connection URL for the web server, format doesn't need ownership of those values, right? Format is just reading them, writing a string, and then returning ownership back. You can imagine it takes an ampersand in the macro signature. So by putting the bind address formatting before where we use AppState, we borrow the state to write the URL, and then we pass the ownership of the state into AppState, and we are done. I think when people start with Rust, this is really frustrating. You're like, why do I have to do this thing? This is miserable, I don't have to do it in other languages. But it's really worth thinking about the advantage. The advantage is that the compiler knows exactly when this value is going out of scope, and it can definitively free it there for you in the emitted executable without any other mechanism at runtime. And it's also good for data races. So imagine we have 8 threads that are trying to write items into a hash map. If we do that in Java, most of us probably realize hash map is not thread safe. You should not do this thing that I've written on the left-hand side. And if we do that thing, we will discover that a pile less elements are written into the hash map than we asked for. And then we'll go and read the documentation and say, hey, I'm not thread safe, this is a bad idea. But substantially, the compiler doesn't stop us. We can write code that is incorrect by construction, and we're stuck. We have to work it out ourselves. On the Rust side, we simply can't write this. And the reason that we can't write this is that we end up trying to write code that mutably borrows the same structure more than once. And this is forbidden. You're not allowed to do this. The compiler says no. So the borrow checker is both helping us ensure that we can always automatically manage memory, and it's helping us avoid race conditions at runtime. Not all of them, but a lot of them. And there are ways of handling this with different high-level primitives in Rust, but substantially, the compiler pushes you in the right direction. It says, now you have to think about this, because what you've tried to ask for doesn't make any sense. So in this case, I'm being a very friendly language user and saying I think both languages get a +1 here. I think it's much easier to start with Java. You don't have this weird friction from the borrow checker. If you've never used Rust before and you pick it up and you try and write a simple web server, you're pretty quickly going to run into this stuff and be really frustrated and confused. But on the other hand, in many cases, you can kind of see the advantage of Rust already, I think. Like this idea that you can get away with the memory being managed for you without paying a runtime cost. That's really interesting. And I think in domains where you're doing things that are really performance-oriented, when you're doing HPC stuff, when you're saying, hey, I'm in a position where I'm actively managing memory and thinking about threading, then it starts to get quite interesting what it's offering you there. And once we've done that, we need a data model. And this is kind of like a small subset of a struct just to think about how we model data in Rust. It's a tile set, so this could be like an instance of this representing a satellite imagery layer or an instance representing an aerial server by a plane or something, different dates of capture, for instance. So we jump in straight away and say, I need debug and clone, which we've talked about before. Serialize and deserialize is using a popular third-party library called Certi to automatically generate JSON serialization and deserialization code for us at compile time, which gives us nice type-checked JSON serialization and deserialization without reflection or anything like that. Here we can see that description is nullable, and in Rust there's no null. Rust has very actively avoided putting null into the language, I guess because of the billion-dollar mistake thing with Java. The idea here is that whenever you have to deal with description now, the compiler is really actively going to force you to consider what happens if there is nothing in there. So again, you're going in this direction of correct by construction. You try and say, hey, just description.value, and say, no, that's not valid. You have to tell me what happens when there's no value here. For bounds, we have a constrained array of 464-bit floating point values. This again will be automatically handled and deserialized by our JSON code. We have primitive integer types from U8 up to 64 as well, so this is 0 to 255 for our zooms. And then we have tile format as an enum. When you first look at enums in Rust, you're like, it's super similar to every other language, but an interesting property of them is that they're actually algebraic data types, which sounds fancy to say, but it really just means that you can associate extra data with any of the variants in the enum. So we could say, for instance, some of these tile formats are compressible, some aren't. So let's say if you have a JPEG, you have a JPEG compression level value on that. We don't see that here, but when we look at the error handling a bit later on, you'll see how that works in practice, and it lends to quite succinct code, I think. The second thing that jumps out is that the implementation, the convert this tile format to string, it's not directly part of the tile format. The tile format isn't really a class or anything like that. And this is kind of a common pattern in Rust. Whenever we implement a trait, an interface, we always do it kind of at arm's length from the definition of the data structure. And here it doesn't really seem to offer you much because they're both in the same file, they're both next to each other. But it lets you do some interesting things from the perspective of reusability. So imagine that we have a tile coordinate, right? So zoom level 21, tile 1010. We would model it like this in Java and Rust likely. And then imagine we're using a third-party library that provides a geographic coordinate type, like latitude or longitude or eastings and northings and meters. There's all sorts of different coordinate types you might want to work with here. And you want to be able to write an API such that wherever you have a tile coordinate, you can use something that can be expressed as a tile coordinate. If we do that in Rust, we have this common trait called from, and it's basically saying, hey, compiler, whenever somebody wants to use a tile coordinate, here's how you convert this other thing to that. Substantially, we can implement a from for any type. We don't have to own that type. So I can use a third-party library that provides lat long. I can implement this conversion on its behalf, and it will just work. In Java, we're probably going to end up writing some static conversion helper function, and ultimately, we're going to end up having to remember to use it everywhere we have to use it. In the Rust case, we just change functions that need to consume a tile coordinate to consume from tile coordinate, which is basically saying anything that can be expressed as a tile coordinate. And that code is then totally generic across anything you can write a from implementation for. And this is quite cool. It leads to very extensible code from third parties as well, and it's leveraged quite heavily in the library ecosystem. With all that said and done, this is kind of what your first path at a request handler to fetch tiles would look at. There's a couple of things that are interesting in here. The first is that on line 4, we're destructuring the request into the tile set ID and then the ZXY coordinate. This happens for us automagically with macros and Axum magic. And the next is that we have all these things that we see can fail. For instance, the bad path error, the DB failed error. And we've just said expect. This is basically a way of getting code out that compiles, but throwing our hands in the air and saying, if there's errors, I don't know what to do, please just give up and bail out. So you can imagine 500s coming back from this. It's enough to show you that the code works, but it is not how we handle errors, and we'll come back to that shortly. While we're here, we can also write some tests for this. So pass Y format, for instance, we want to make sure, that we handle Y formats not being passed correctly. In Rust, we have a built-in testing library. We don't have to pull in anything like JUnit or anything like that. We just use it. We also write tests in the same file that the surrounding module is expressed in as a nested module, pull in all the parent symbols, whack a test macro on it all, and it all just works. And this is nice. Again, everyone writes code in the same way. The test is always nicely co-located with what it is testing. And I think at this point, there's a couple of things that have jumped out that are like quite nice with Rust. And the big one is the idea of forcing you to handle error cases, both in the result and option case, where you say this thing is fallible, I have to do something with it. So far, we've just said give up, but we had to do something with it. And in the option case where we have a nullable, again there we can just say give up if it's not there, but we've had to actively tell it to give up. We haven't just let it go through to the keeper. So we haven't connected all the dots yet, but I think we're starting to see that there is some use in this way of modeling fallibility. And hopefully you're like, oh, those are some interesting ideas. Maybe we're excited about all this crap that people have been carrying on about Rust for all this time. Now imagine we've got this thing, we've thrown it together, we have our crappy error handling, and we want to pull request it into some monorepo at our company. So we end up with our first code review experience, and our colleague Jeff, who has, for some reason now, a broken image as his GitHub logo, is saying this error handling, it is awful and is not very idiomatic for Rust. Please fix it or I will quit the company and my career. And Jeff is a bit dramatic, but obviously there's something we need to do there. And if we go back and look at what we were actually using in that request handler to get a tile, we have a function that gets a tile set, which is the metadata about the tile layer. And we have a function that gets the tile itself. One returns data from the database, the other returns imagery from S3. And what we've done well is that we've said that these both have their own error types. So in the first case, we return a DB error. In the second case, we return a storage error. And looking at those types, we can see we have branches for the user gave me an invalid value, the value was not found in the database, and so on. But substantially, they're two different things. And in our getTile function, we need to handle these, right? We need to not just say expect that it succeeded, we need to say what to do if there's an error. And your first pass is going to be something like this. You're going to go through and say, hey, let's match on the result after we await the future. If it's success, great, take the value. If it's bad and it's a DB error not found, return a 404. If it's a bad and it's a DB error SQLX, return a 500, and so on and so on. And this works. It's very verbose and like kind of a Golang way, I would say. But it's not very reusable. You can imagine that what we should do in response to a DB error not found is going to be common regardless of the API endpoint, right? Like if I said, get me the metadata about a tile set, and I ask for a tile set that's not there, I'm going to want to return a 404. So this is really duplicative and kind of not very pleasant to read. The Rust way of handling this is to basically say, look, we have this layer of errors that are specific to different services within our application. Let's roll them all up into a common app error. So down here we can see this app error has bad request and validation in the top part, but then down here we have an error type for the DB error we just saw from our DB handling code, and a storage error for the S3 handling code. And that from annotation there is saying, hey, can you automatically implement the conversion from a DB error and a storage error to app error for me? So now whenever we want to use a DB error or a storage error, we can also treat that thing as an app error and it will just work. Once we've got that, the final piece that we need is a way for us to treat app errors as HTTP errors. So we can say a DB error not found is a 404 regardless of where you express it. In Axum, we can do this by implementing an instance of the into response trait for that struct app error. And it's basically exactly the mapping we saw before, but in one place and kind of at arm's length from our request handler. And once we've done that, we can write a request handler like this. So now we have getTile. We say it returns either something that can be converted to a response or an application error. And when we go and call things like getTileSet that don't return an app error, but actually return a DB error, Rust is automatically taking the failure path and saying, hey, DB error, we convert you to an app error, we convert to a HTTP response, done. So we have very clear type-checked error handling off to the side from our handlers, and we can just read the happy path in the handlers themselves. This is also not to say that you can't handle these cases differently. So if you say forget tile, DB error not found, we handle it differently. We handle it, for instance, by returning a base imagery layer. We can map out just that subset of the error here and then pass the rest through to the keeper. But substantially, the common case is handled in one place, and the compiler makes sure that we've covered all the branches for us. If we think about the Java variant, this is probably not perfect Java, but it's kind of where I landed. What I think generally happens is we go and try and catch the errors that we imagine when we write the handler the first time. So here we know tile format might fail. We'll return a 400 for that. The rest we just let go through to the keeper. And then we whack in a global exception mapper as well and return 500s. And then as we run this service, people come back to us and say, hey, I tried to get a tile image. Instead of getting a 404 for an invalid thing, I got a 500. And then you go and add more and more mapping. This works, we get there in the end, but the compiler hasn't forced us to get there at the beginning like it would with Rust. So here I'm going to arbitrarily award Rust 4 points. I think this is great. It seems really frustrating again when you get started. You get constantly thrown under the bus by the compiler. But when the thing compiles, there's this whole class of errors that you haven't even been forced to suddenly deal with at runtime because they were essentially pulled forward in the developer lifecycle. Once we've done all that, once we've fixed our error handling, we've got the other bits in place, we're going to want to deploy this to production. Now, in Java, this would be, not a no-op. If we ignore all the managing of Kubernetes and clouds and all that fun that developers don't really like, I think, we have a jar, we can run that anywhere. In Rust, we have a binary. We have to build the binary for the target we are trying to target. So on my Mac, I run cargo build release. I want a nice fast binary with all the nice optimizations applied. And I get a Marco out, which means I can only run on my fancy Mac. I can't run on a Linux server. So we need to build it for Linux. Fortunately, it turns out that Rust Up, which is the version manager for Rust compiler installs, has the ability to do cross-compilation to other targets. So you should be able to say, hey, Rust, give me a target for ARM64 Linux with the GNU runtime, build it on my Mac, and I'll ship it there. And this is kind of cool because you don't have to run builds fanned out across different build infrastructure. You can just say, Rust, please build it for that target. And it's cool until you try to do it. And the thing here is that a lot of Rust libraries, a lot of Java libraries, a lot of libraries in general depend on native code. And whenever you try and cross-compile things, even if you have this nice compiler in the front that can notionally do it, if those libraries that you were depending on depend on something that's not available on that system, for in this case, my Mac doesn't have OpenSSL Linux headers and linked binaries, unsurprisingly. The compiler just gives up. It says, look, I could compile your Rust, but this other thing, you're stuck, sorry. And the reaction to this with Rust is you can kind of dig into the dependencies and you can try and avoid your need to use those native libraries. In this case, OpenSSL has been pulled in by Rust S3, which depends on Tokyo native TLS, which uses OpenSSL. We can think really hard and read through our dependencies and work out if we change that to Rust TLS, we end up with a TLS-only implementation. This is kind of a pain, and you constantly break it because you discover you want to use some other library that has a native component. Realistically, what most people do is have GitHub run for different target architectures, 3 different workers, Linux x86, 64, Mac, and Linux ARM, and then fan it all in again, which costs more and it's more configuration to manage, but it doesn't break all the time. For Java, there's no slide here. Obviously, Java is build once, run anywhere. This is something that people talked a lot about when Java came out because it was kind of novel. And you just forget it now these days, I think, the idea that you can build a jar and just run it on any infrastructure. But when you start playing with Rust and trying to ship it, you're like, oh yeah, that's actually really, really helpful. So 3 points to Java because there's none of the issues here, right? Like you just ship it, it's done, you have your reference jar. Now, once we've got that going, we can imagine we ship it to our infrastructure and it runs. And we don't really have any observability. We can see from our fancy platform load balancer, we get some 503s back. Your service is dead. Please fix it. People in support probably start shouting at us. Our boss probably shouts at us. No one's very happy. We have no idea what's going on, right? So we say, oh yes, actually, we need some observability for this. And this is one of those things where Java is really, really good, to be totally honest. If we're using Quarkus, we have the OpenTelemetry extension. Everything in Quarkus is already nicely integrated with OpenTelemetry, all of your HTTP clients, all of your database clients, it just works. We send the data somewhere, we might send it to Datadog, we might sell it to the OpenTelemetry collector and push it out to Prometheus and Elasticsearch and wherever we want really. Everyone speaks the same language. And we can also do really fancy things at runtime with observability, like use Java agents to dynamically insert themselves into our code. For instance, if you use the Datadog agent like here or the OpenTelemetry Java agent, we can automatically add runtime profiling for you. It just happens. This is a nice advantage of having a runtime and not having a native binary that shakes out at the end of the whole process. And this all just works. You don't have to think about this. Everyone does it in the same fashion. It's easy. You're kind of on the happy path. You can also do jazzy things, in Quarkus at least, like add dev services. You say, hey, when I run it in production, I want Datadog or Dynatrace or whatnot, but locally I need something. Can you give me something? You end up in this case with Grafana, Loki, and Prometheus. It all wires up, it all just works. It's really this simple. There's nothing more to it than this, right? And we can also do other fun things. I quite like observability, so there's a bit more of this. If we're in Spring, we're realistically using micrometer for metrics, probably micrometer traces for tracing, maybe as a facade over OpenTelemetry. Just works, everything does it. We can do request correlated profiling, so we can say, hey, I want flame graphs back for just my get tile endpoint or just my database endpoint. Don't have to work very hard for this, everyone supports it. And we can use cool built-in tools like the flight recorder and mission control to get really detailed analysis of what the runtime is doing. Now, the Rust side of things is a bit more of a mess. And I say this as somebody who works on OpenTelemetry Rust as part of my day job. The first big issue here is that the community is kind of fragmented around these two different libraries. The first is tracing, which is part of the Tokyo project. It's for structured logging and request tracing, but in process. So it doesn't help you get request tracing across different services, which we want. And then there's OpenTelemetry, which cares about getting request traces across things between services, but doesn't have a log front end of its own. And then there are bridges that go in both directions. So the kind of real actual pattern that people should be following now here is to use tracing, use a tracing subscriber to push the tracing data into OpenTelemetry, push that onwards into your observability provider. But there's all these other side quests and combinations of things that you can get distracted by. And again, as somebody who works on this, it's really not obvious to get started. You end up doing all these different things, trying to work out how it should be, and eventually, hopefully, land on this pattern. But it's fiddly. Likewise, the code to wire things up is rather involved. There's a lot of things you can get wrong here. So observability, absolutely Java. It's just way easier. Everything works very well out of the box, and the runtime is a massive leg up. So with all that said and done, we can imagine we have a thing now that runs, it works, we can tell what happens when it breaks. But I started this whole thing by saying, like, hey, we care about performance, so Rust is kind of interesting. So where do we land? On the Java side, once you start talking about this performance, you're going to go Google, you're going to do some GC collection tuning, you're maybe going to use Crack to snapshot your application and make it start faster. There are all sorts of exciting knobs you can twiddle here. On the Rust side, there's nothing. There are no knobs, you have no runtime, you don't think about it. One other interesting thing you can do with Rust, and this is kind of like a side quest, this isn't a thing I'm suggesting, but it kind of highlights the control that the language gives you that is difficult in other languages, is thinking about how you share data across the different cores of your CPU. So imagine we want a tile cache. We want to be able to say, hey, if somebody comes in and gets a tile we've already fetched from S3, just return it from in-memory. In Java, we're going to make a cache, or we'll use a caching library. We'll share it across all of our different requests, and the library will have some internal synchronization mechanism that's basically saying, hey, you know, I know I'm being used across threads, so I have to do some locking or what have you to make that work nicely. There's some small overhead. On the scale we're talking about, we probably don't care much. In Rust, you can do weird and wild things, like say, hey, instead of doing that, I don't ever want data to need locking, and I don't ever want data to move between cores. So let's hash our incoming tile coordinates, for instance, across all the cores we have. Let's immediately pass them off to the thread that handles that. And by doing that, we can say that thread can use a cache that doesn't have to be thread safe because it knows it's not being shared. So there has to be no synchronization. And it also gives you the advantage that you have very good cache behavior with the CPU core itself because you never have data that has to be synchronized through the lower levels of the cache, the system RAM and whatnot. It's all kept really local to the CPU. To be clear, this is completely unnecessary in almost all use cases, and it also leads to other cases where you end up underutilizing your cores more because you don't let the cores work on other threads work. But in some cases, it can be super valuable, and it's something that you can express in Rust that would be very difficult in Java. So how do they actually compare? And I have some numbers here. This is all like very scientific, tested on my laptop. I profiled both of them reasonably hard and fixed things up that were obviously broken, but I didn't go much further than that. For throughput and latency, they actually came out really close. And to be honest, I was a bit bummed by this. I was hoping there was like a real kick in the tail latency for the Java one. I think part of the reason for this is that the laptop has 64 gig of RAM and there's really not much GC pressure there. I would expect there to be a bit more tail latency there if we jammed it down into a smaller container. But you can see that out of the box, Java is very competitive. When we look at memory, it's a bit of a different story. We end up using dramatically more RAM for Java than we do for Rust. I think this is unsurprising. This is the cost of having a runtime. And it's a similar story with the startup. I mean, Rust is effectively everything has been compiled ahead of time. Everything has been optimized ahead of time. In Java, this flexibility of having a managed runtime means we're doing a lot more at runtime. This means we have a lot more to get the thing going. And the binary sizes are a bit tighter as well. So here I've got, I don't know if you've noticed the motive. When Java wins, there's a coffee, and when Rust wins, there's a crab. In this case, we have a crab drinking a coffee. So once again, everyone wins. And the point I kind of want to make is that you can get really good resource utilization out of Rust if you need it. But Java is really fast without any of this stuff, without of having to pay the cost of the borrow checker and thinking really hard about our application construction and whatnot. There are cases where I think you really definitely would use Rust because of these things. For instance, if you were doing something that's heavily resource constrained, the kind of classic modern approach is you're doing serverless, you want to use AWS Lambda, you simultaneously want the thing to start very fast and you want it to use very little RAM because that's kind of the cost knob. Rust is just obviously a better choice. At Datadog, we instrument customers' serverless functions for them so you can get observability out. We used to do this using Python and Go. We rewrote the whole thing in Rust. It is a really nice story because it's just direct cost savings for our customers. I mean, they're effectively paying to run this extra piece of code on our behalf, so if we can make it use less time, use less resources, it's a nice win. But I think in many cases you just don't care, right? Like you have the RAM free, you can throw it at it. You don't mind about this trade-off for efficiency because you're probably a bit faster at development time. It actually works. I don't have much time to like drag around on my map viewer, but you can see here is a lovely scroll across the Swiss mountains that I set up from the top of these two services. In terms of kind of like arbitrary numbers, they're about the same size. You plug a lot more together to get the Rust variant going. There's a bit more code. And if you kind of zoom out a bit, I think the things that you really, the way to really think about the difference is this. On the Java side, the runtime is doing heaps for you. It has a lot of complexity. The runtime is absolutely ridiculous. It's an amazing piece of engineering. It lets you do a lot of stuff and is very, very fast with very little effort from you. The ecosystem is amazing. The tooling is amazing. Everything is stable. We've been doing this for, what, 30 years now? Observability, which I personally care about a lot, is best in class for languages, I would say. On Rust, you shift a lot into the compiler. You shift a lot into your own domain at compile time. This gives you some advantages. Things tend to be more correct at runtime because of that. You end up with little, small, very efficient binaries. And you have more control. In situations where you need weird low-level control to tie things to particular threads to avoid data moving around, you have that in Rust. So what makes sense? I think if it was me and I was working in a company like everyone else that's doing Java Web Services on top of databases, it's kind of hard to imagine picking up Rust. Like, it's not going to give you enormous improvements in developer efficiency. You're going to have a bit of a friction there to get started with. There's probably not a huge driver there. On the other hand, if you're already working in a domain where you're resource constrained, where latency has become a problem within the Java universe, it's kind of like the next thing to reach for. And that's all I got. I've run slightly over time. I hope no one's too traumatized by that. There's some links behind this 2D barcode. I'll post them in Devoxx Companion later. Thank you for hanging around to the end of the day, and enjoy the rest of the evening.